Hello, my name is Sawyer West. I am a student at Vanderbilt University pursuing a master's in computer science. Today, I will be talking about my first project in my master's program. Disclaimer 1. My project is rough and should not, under any circumstances, be used as a reference for best practices. Disclaimer 2. My code is heavily inspired by resources on the web provided by the professor and provided by documentation. Full links to these resources are provided in the code. Without further ado, let's begin. When a country is trying to increase the lifespan and health span of its population, it will have a finite amount of resources to invest in said goal. Knowing which factors to invest in for the greatest overall effect will increase the efficiency of a government's investment. It is important to distinguish between lifespan and health span. Those who live a long time have a long lifespan, but those who feel healthy and happy for a long time have a long health span. These spans dwindle when the body accumulates damage over time. Scientists agree in total that there are 8 different age-related damages. This was first proposed by Aubrey de Grey. While progress in the field of longevity is making progress to protect against and even reverse aging, with societal changes, the amount of damage the body is exposed to can be reduced. For more information on the field of longevity, I suggest the following books and podcasts: The Telomere Effect, Lifespan, Life Force, and the Andrew Huberman Podcast. Furthermore, if you are interested in the philosophical implications of living forever, I would suggest looking into the video by C.G.P. Gray called The Fable of the Dragon Tyrant. My goal was to use machine learning to rate the effects of health changes we can make in society. If changing one factor has a large positive effect on many other factors, then it is said to have a strong influence. Alternatively, it is said to have a weak influence. The relative influence is given a numerical value. Furthermore, using this influence value, we can rate all of the factors which have an influence on a variable in consideration. This full scope is incredibly computationally expensive, and for the sake of having a realistic deliverable so I can pass this class, we will create models around predicting the longevity of populations. The data I will use was collected by the WHO and the United Nations from 197 different countries over the course of 15 years. It has 20 measured factors and 2,938 rows. If we want to indirectly reduce, for example, alcohol consumption, there might be some factors which are deemed influential by the machine learning algorithm, and others which are not. The measure will be the strength of influence. If there is a high cost to directly influence a factor, but a low cost to indirectly influence a factor, then the model has a very high value. A confusion matrix would allow us to predict and weigh this discrepancy in dollars, but these are normally applied to classification problems. Instead, we will use the root mean square error to compare model performances. Let's consider the code. I used Google Colab to code, Google Drive to store data and drafts, and GitHub to store final drafts. At the top, we see the linking of the Google Colab file and the Google Drive. Next, we import table and visualization libraries, followed by machine learning libraries. Finally, we load in the dataset for the project. For my own sanity, I checked to see the data was loaded properly. Checks like this will be done numerous times but I will exclude the rest of them for the remainder of the presentation. Refining the data dictionary for the model is a multi-step process. First, we want to identify which data types are mistypes before we correct the problem. Second, we want to identify which columns we don't want in our data set. For example, if a country changes its name by one letter, we don't want our model to catch on fire because it doesn't know what to do. Secondly, we don't want an expert telling our model if they consider a country developed or not. Next, we want to visualize the data with graphs so we can formulate hypotheses about our data. It seems that there's not a correlation between adult mortality and total expenditure. This comes as a surprise given that intuitively one would expect more resources is indicative of less death. The same unintuitive non-correlation holds when total expenditure is graphed against polio and hepatitis B. However, the amount of alcohol consumed is strongly correlated with the years of schooling. It is unclear if this is due to people with more education having more resources to spend on alcohol, or if frat life is influencing my dataset. For the feature engineering, I needed to make the data easier for the model to understand. Hence, I condensed all diseases in the dataset into one diseased population, and converted all measures into per capita measures. Finally, I removed the collinearities, which are the building blocks of these new features, from the dataset. I then had to rework all of the per capita measures back to population measures because my model had a hissy fit when presented with continuous values. Now that we are finished refining our data dictionary, it is time to split the data. I decided to use a 4:1 split and a 10% holdout for the training data. Now, we define the pipeline the data will run through the output model. Since we have no categorical variables in the dataset, there only needs to be a single numerical pipeline. This pipeline was reused 3 times for 3 different models: logistic regression, random forest classifier, and gradient boosting classifier. Next, we set up our tuning grid. The grid was then fitted to find good hyperparameters for our model, and then we applied these parameters to our model. Now we evaluate the performance of these models. The evaluation indicates that the random forest classifier modeled the data better than other models. I then took a look at what happens when I remove the feature engineering from the data. And it turns out it doesn't really go and change the model performance in a way I would like to see. All of my features were hindering model performance. Thank you for watching. For this presentation, I used images that I do not own. They are classified as free to share and use under Creative Commons. However, that doesn't really apply to this presentation as this is an education video. The requirements are much less stringent. Ciao.